Is that good? Everyone see that?
Yes.
All right. Well, thank you, Claire, for the introduction. It's nice to be part of this session, and really enjoyed the talk so far. So this, I'll be talking about work actually with Claire that she and I have been doing this past year. And the title of this is a comparative study of differentially private synthetic data algorithms from the NIST PSCR Differential Privacy Synthetic Data Challenge. So this was some work that NIST asked us to do following on a challenge that they ran 2018 and 2019, where they were looking for competitors to put out, to come up with ways of synthesizing data sets that NIST had published, and then they were scored on some different metrics. And the idea was they really wanted to increase kind of the field's knowledge of the mechanisms that are out there, and try to incentivize people to work on this problem more. So as Claire said, this kind of falls in the we need more use cases category. And I think it's been interesting to see kind of what has come out of this so far. And I know that NIST actually is planning on running a second one of these. So if you're someone who is working on differential private synthetic data or is interested in this topic, definitely keep your eyes out. I think it'll probably happen sometime later this year. So yeah, also just a thanks to NIST for supporting this research. This talk is going to be pretty high level. There's kind of a lot of details if you look at the paper, but I'm going to be giving more of a high level view of the algorithms that were used, and then the way we evaluated them, and the takeaways for data practitioners and providers who might want to use these algorithms in the future. So before I go to the challenge, I'm going to give just a couple background slides. Claire did a really nice job actually of talking about synthetic data and differential privacy, but I'll give a couple slides as well. So synthetic data was originally proposed by Don Rubin back in the 90s. And it's a pretty straightforward idea. I've given this schematic here to kind of give you an idea. But basically you have some input, which is X, and maybe some prior information. And what you do, the way I've laid it out here, is in a Bayesian framework, what you do is you sample some parameters based on this information, and then you use those in your model to then sample new data values, new X values, and then you release that as your synthetic data. And I've done this very generally here because, as you've seen already in the talks, there's a lot of different ways to do this. It can even be images or text or any of that kind of stuff. You can do this in a non-Bayesian way also, where you just directly estimate the parameters. And in theory, without the differential privacy, the protection for synthetic data is just from the fake nature of the data. Okay, so, and then differential privacy, what is this? So again, I've laid out the schema similar here because I'm going to be talking about combining the two, and I was hoping that you would see the similarities. So in differential privacy, you have a similar setup where you feed in an input X, and then you have this F, which is a random function. This is actually the function that has to satisfy differential privacy. And you have to induce a certain amount of noise through this F. So intuitively, the amount of noise that you induce needs to be proportional to the impact any individual can have on the output, which is also known as the global sensitivity. And then the outputs from this function or mechanism, as they're often called, are differentially private. Optionally, you can run this through another function, say G, and produce another output. And there are theorems that show that this second output is also differentially private. So this is useful for synthetic data if you think about perturbing the parameters of the model and then synthesizing data based on those differentially private parameters. The data will also then be differentially private. So why should we combine them? On the one hand, the theory of synthetic data is that it's fake data, but in practice, that's not always so true. I want to actually give a nice example of how that might fail. Other examples of this are models that essentially reproduce the same data. This is, may sound unlikely because you're drawing data from a random distribution, but if you use a really complex model, it's actually quite easy to get data that are the same or really similar to the original data. And so at the end of the day, you're really not protecting any privacy, even though it's fake. On the other hand, for differential privacy, there's this problem with query-based systems where someone is just querying information from the data. The problem is every time you do that, you use some of your privacy budget and eventually you run out. And so with synthetic data, instead, you just put all of your privacy budget into creating the synthetic data, and then people can do whatever they want with it. So you're likely to lose accuracy on any particular query, but it's really helpful for exploratory applications where people really just want a data set to play around with, and they don't have specific questions that they're trying to query. Okay, so now I'm going to talk about the challenge. So as I said, this was 2018-2019, and it consisted of 3 matches that they ran during that time. What they did was they published training data sets, and they asked competitors to devise algorithms based on these training data. And then competitors submitted their code, and it was run on holdout test data that had the same schematics as the training data, but different values. And what they also had was expert reviewers who judged whether the algorithms actually satisfied differential privacy. So the competitors had to submit full descriptions of their mechanisms and proofs for why they satisfy differential privacy, and then these were evaluated. And then the actual scoring was using 3 bespoke accuracy or utility metrics, as I'll call them, that NIST came up with. And then they were tested on multiple levels of epsilon. So they were also interested in seeing how these algorithms performed as you changed epsilon. So in this talk, I'm going to cover the top 5 performing algorithms from matches 2 and 3. I'm not going to talk about match 1 because it was the same data set as match 2, and so a lot of the same results came out of that. And between match 2 and match 3, there were 6 total algorithms that performed in the top 5. So here's the data sets that were used. So for the first 2, this was the San Francisco, excuse me, the San Francisco call for service data. So this is fire data that San Francisco has made public. And NIST used different years for the training and scoring. And then in match 3, they switched to the public 1940 census data, and they used different states for the training and the scoring. And the scoring data sets were not publicized, so people wouldn't know what they were going to be tested on. In match 2, the epsilons were set fairly low, 0.01, 0.1, and 1. And then in match 3, they were raised to 0.3, 1, and 8. Okay, so I'm going to spend some time talking about the algorithms that were used, and I think it's helpful to break these down into the non-parametric versus the parametric algorithms, as I'll call them. So Claire actually also, I didn't realize she was going to walk through all of that, but she set this up very nicely. So the non-parametric algorithms work primarily by creating these cross-tabulations or histograms of the data, and then perturbing those bins, typically using the Laplace or Gaussian mechanism. Oh, and I should mention actually the NIST challenge. It was epsilon delta privacy. Some competitors chose not to use delta, but they had an amount of delta that they were allowed to use as well. So some people use the Gaussian mechanism, some people use Laplace for the non-parametric approaches. The main issues that you kind of have to figure out when you're using these types of approaches are what relationships to preserve. So this gets to the idea of collapsing the domain space. So if you just look at every possible bin, every possible combination of every variable, it's a huge sparse space. And so really, if you want to have good utility, you have to collapse that in some way. You have to basically assume some of those are 0. So what you do is you do a lot of work with public data or the training data in this case to try to determine what relationships are worth preserving in the data. The second thing is how to allocate the budget. So, naively, you could simply allocate the budget evenly across all of the bins, but it might be better to separate the budget and put more on, say, variables that you think are more important in the data. And then lastly, what to do with continuous values. So here, if you have a continuous value and you're creating a histogram, you have to decide where you're going to bin the values. And so again, this comes back to working with the public data. You have to have some kind of prior information because you can't look at the actual data to inform you on those bins. So the second general approach is the parametric synthesis. This works by creating a model for the data, or having a model for the data, and then perturbing the parameters of the model, and then drawing samples from the model with those noisy parameters. So the big questions here are, how do you choose a good model? There's a lot of different ways you can do this, and in non-differential privacy synthetic data, what you do is you model the actual data, but you can't do that here. So you have to have some other way of choosing your model. And then the other big thing that you'll see is just computational feasibility. The parametric approach relies on kind of intelligently sampling from a really large high-dimensional space. And so computationally, that can be pretty taxing. So for both of these, I would say pre and post-processing are pretty significant. What I'm calling pre-processing is that working with the public data to try to figure out the relationships that are worth preserving, or the models that you should use. And then post-processing is anything you do after you've created the data to try to, say, enforce consistency or those types of things. Okay, so to get into the actual algorithms that were used by the competitors, so there was 3 of the 6 that I'll talk about that were what I'll say are non-parametric approaches. So the first was Team DPSyn, and what they did was they clustered variables based on their correlations, and then they perturbed the 1, 2, and 3-way marginals within each of those clusters. And then what they did was they implemented a way of post-processing to enforce consistency to make sure that the 1, 2, and 3-way marginals were consistent with each other. So they did a lot of work on the front end of the clustering. The second one was the team Garden 999, which was actually pretty similar to DPSyn, a pretty similar clustering approach. But rather than perturbing the 1, 2, and 3-way marginals, they perturbed the whole joint histogram within each cluster. And so they're working with a larger space. And then what they did was they set a threshold for post-processing. They set a threshold where any bins that counts below a certain threshold were reduced down to 0. So this was a way of essentially reducing some of the noise in the model. Third was Team PFR. So they categorized variables more based on domain knowledge. So they did more work looking at kind of the background of the data and what variables should be related, rather than just looking at correlations. And they, within each of these categories, they perturbed just the 3-way marginals, which they probably did this because that was one of the ways that NIST was explicitly scoring, was based on 3-way marginals. And then they allocated the budget proportionally to the number of variables in each of these categories. So they didn't just do it equally. So all of these methods, the big work was on the front end of looking at the training data and figuring out, what parts of the histogram to preserve and how to allocate the budget. So now for the other 3, these are what I'll call parametric synthesis algorithms. The first was Priv-Bayes, which is maybe one of the more familiar ones from these in the literature. So what they did was they essentially scored each pair of variables based on their correlations, and then they perturbed these scores and created a Bayesian network. So they essentially treated these scores as parameters for the Bayesian network. And then they sampled from that and then did some post-processing afterwards to enforce consistency. The second one was Team R. McKenna. So this was an interesting one. It was a hybrid really between non-parametric and a parametric, I would say. So they did very similar first few stages to the non-parametric ones, where they clustered variables and they perturbed the 1, 2, and 3-way marginals pretty similarly to DPSyn. But then rather than simply sampling from those noisy bins, they layered a graphical model on top of the noisy marginals and sampled through that. And they actually, as you'll see, ended up getting fairly good performance. So it was an interesting idea to combine these two. And the last one was UCLA NESL. And they did Wasserstein generative adversarial network approach. So, so we heard about a little bit in Juan's talk with the GANs. This is where you're fitting these competing networks, and as was brought up in the questions, they used a perturbed gradient update to guarantee privacy. One of the things about this approach is that you know, because there's a fixed privacy budget, it terminates this whole GAN approach, which is updating, terminates when the privacy budget is exhausted. So the PRIV-based in the UCLA one required fairly significant computational resources. And so, as I mentioned before, that's often one of the things you'll see with parametric approaches. Okay, I'm not really going to go into detail on the utility metrics that we used, just for the sake of time. I encourage you to look at the paper if you're interested. But what we did for our paper was we expanded the set of evaluations beyond the original 3 that NIST did. So we worked in a number of other metrics that are pretty common in the literature for evaluating synthetic data. And what we ended up doing was binning these different metrics into 3 categories. So the ones that I'll call kind of low marginal distribution metrics, so based on univariate or 3-way marginals. The joint distributional metrics, which are really looking at, you know, all the variables simultaneously or a large portion of the variables simultaneously. And then the correlation metrics, which are the most specific, that are saying, you know, if I fit this one regression model on both the original and the synthetic data, how similar are my coefficients? So this is, you know, the really zoomed in view of utility. So again, I'm, you know, just for the sake of time, not going to go through the many tables of results that you can find in the paper, but I tried to synthesize them here into this table to give you an idea. So in match 2, we just had the first two categories of utility metrics. And the top performers were pretty similar between the two, and but there was no real one clear winner. I'll note that PFR was the one who actually won the NIST Match 2 challenge, but we found when looking at the broader suite of metrics that DPSyn and PRIV-based also were relatively comparable when you looked at the full range of metrics. One of the things I'll note here is that there was just very little variation in Match 2 between the competitors and also between the different levels of epsilon. So the utility was pretty flat, even as epsilon increased. And I think this was in part because the data set was a pretty tricky data set to synthesize, and also because the levels of epsilon were fairly low. But again, there was not any kind of clear best performing algorithm in Match 2. In Match 3, there actually was a pretty clear best performing algorithm, which was the R. McKenna one, which was a combination, as I said, of non-parametric and parametric. And they pretty consistently did the best across the first two categories, the marginal and the joint distributional categories. When we zoomed in on correlation metrics, you know, then we got more varied answers. And again, this makes sense because these are highly specific utility metrics, and so you would expect that, you know, competitors who are designing their algorithms for very general synthetic data, you know, might miss one or two relationships, for example. So this is just to give you an idea that, you know, you might perform well, your synthetic data might perform well on one type of metric, but not on others. So the other thing I wanted to show you is these utility plots that we included in the paper, because I think this is a really nice way to visualize the information. And so I just wanted to give you a couple of examples. And we got this idea, we borrowed this idea from another paper that recently came out, which I would encourage you to look at, which also talks about ways to assess utility for differentially private synthetic data. And so what we have here are these, on each of the axes here of the chart, is one of our utility metrics. And as the filled in areas expands to the outside, it implies that you have higher utility. And then the different shaded regions are the different categories. So the red are the low level marginal distribution utility metrics, and the blue is the joint, the full joint metrics. So one of the things I wanted to highlight here is that if you look at the left with R. McKenna, as I mentioned, there's almost no change as epsilon changes. Actually, I realize there's a typo. This is match 2, so the epsilon should be 0.01, 0.1, and 1. But if there was change, you would see different shaded areas, but you just see one green kind of triangle. And it's because the utility is equivalent almost for all levels of epsilon. You do see a little bit of variation if you look at the one on the right. You see that there's a little bit more utility, a little larger shaded area of the green as epsilon increases, which suggests that the algorithm is improving somewhat as epsilon grows. But the other thing to see here is just that neither of these are performing super well. And as I said in match 2, that was kind of the story for all the algorithms. It's different when we look at match 3. So here we see much better performance, as I said, and better performance kind of across the board. We also see that for both of these, with a couple exceptions, for the most part, the utility is increasing as epsilon grows. And remember here, we have a larger range of epsilon, so it makes sense. We're starting to see a larger range in how much noise is being added. I also will highlight here, you can see the point I was making about R. McKenna performed the best, particularly on the red and the blue type of metrics, which were the distributional ones, whereas Garden 99 on the right did better on the correlation-based ones, which were the yellow. So these plots are just a nice way, I think, to visualize a lot of information all at once. Okay, so I do want to spend a decent amount of time talking about the takeaways from this, because I think we wanted this paper to be very practical, and we wanted to be able to give practical advice for people who are thinking about using these algorithms or want to know kind of the status of DP synthetic data and what needs to be done. So I have a number of takeaways here. So the first is that the best performing algorithms really relied on intelligent pre-processing and budget allocation to reduce the output domain. So this is where I was saying, the best ones were the ones that cluster the variables, that reduce the space that they were trying to preserve. And really a surprising amount could be done with just a Laplace or Gaussian mechanism on a simplified histogram. Those were pretty consistently the best performing metrics. Now that does assume you have access to good public data, which is not always the case. But if that is the case, at least from this application, those are the ones that did the best. The second thing is that the parametric methods, or the approaches that have a lot of post-processing, didn't show as clear of improvements with rising epsilon. So, I'm sure many people have seen this kind of risk utility or privacy loss accuracy trade-off curves, where as you increase epsilon, you will see your utility increase. But with the parametric models and the ones that use a lot of post-processing, there's a lot of other noise that's coming into the model, and so you don't get as clean of a picture between privacy loss and utility. So if that's a desire for someone who is devising these methods, if you want to be able to point to a clean utility trade-off curve, you'll probably prefer a non-parametric method with minimal post-processing. The third thing was that, as I said, the non-parametric methods require extensive pre-processing, whereas the parametric methods require more significant computational capabilities. And I think this is a helpful trade-off to think of if you're a data provider, someone who's thinking of using these methods. You should think about, what are your resources? Do you have the ability to do this kind of extensive work with public data, or do you have the resources to do some of these more complicated computational tasks? And balance those against each other, because a lot of times that's what's happening. Now, you could also do both, but a lot of times you're choosing between one or the other. The next takeaway was that pre-processing and budget allocation can actually be general or narrow. So I didn't really touch on this. We touch on it more in the paper, but some of the competitors did a fairly general pre-processing where they just looked at correlations and they didn't really tailor their method to any one particular thing. And they did better kind of more generally. When you look at some of the other metrics that we brought in, some of the more specific metrics, they kind of captured a broader space. Some of them, on the other hand, were very narrow. So they said, we're going to tailor our method specifically to the scoring metrics that NIST published. And you could tell the people who really were tailoring theirs to that. So even though synthetic data in general is a very broad topic or a broad approach of generating this whole data set, there's still ways that you can tailor it to either be more narrow or less narrow. If you know that there's like specific things that you want in the data, there are still ways to tailor it that way. The next point was that really from what we saw, the experimental methods, namely the GANs, just achieved much lower utility than the simpler methods. I also didn't really highlight this in the results, but there was one GAN method out of the 6, and it performed very poorly compared to the other ones. And I think our takeaway from this was that it was due to both some extensive clipping that they had done and also the fact that the algorithm, it didn't seem like the algorithm optimized, or that was our guess, based on the way it performed. And this is probably coming from the fact that you have to cut it off when the privacy budget is expended, or at least their algorithm had to be cut off when the privacy budget was expended. And so it might just not optimize, and then you don't get very good synthetic data. And so actually, I'm very interested to look at Juan's work. I haven't seen that before of their different approach to doing GANs, because I know this is a very popular method right now. And so it was somewhat surprising to see it perform poorly in this challenge. It also, unfortunately, is very computationally burdensome. So this method, the one that was used in the challenge, required or used a GPU, when one of the things that we highlight in the paper is that a lot of people who are not experts in computing might not have access to that, and so this might not even be a method that they could use. There was actually a second GAN method that was submitted to the challenge, but their code, NIST couldn't even get their code to run. So there's things that need to be worked out here in the computational realm. But I do think a really big question for GANs will be, how do you handle this problem of it terminating potentially before it's optimized? And then the last point, which I want to highlight, just to end on an optimistic note, is that in match 3, particularly as we looked at the higher levels of epsilon, some of the algorithms performed fairly well. They produced fairly high quality and usable synthetic data. So I think that's something we should take away from this, that there's actually pretty reasonable results that you can get with what we have so far, and there's a lot more we can do. But I think DP synthetic data is certainly an approach that we should keep pushing on. So that's all I have. Thank you so much for listening, and I'll take any questions.